Hi everybody. I am sorry. I am going to be showing you about the periodic table today. I will show you where to find this page here, which also has a back, and it has a super cool link that I think you are going to find as cool as I do. At least I hope so. Okay, so we are on my Google Classroom. Of course, mine looks different than yours because I am teacher. And we are going to Let's Explore Chemistry Web Quest, which let me just, while we're here, move this up above chemistry experiments. There we go. Okay. Okay, so you will see the PDF. Let me scroll back up. Okay, Let's Explore Chemistry PDF. And it gives you two links. So the first link is to watch a video about the genius Mendeleev's, I think is how you say it, his periodic table from TED Ed, and then answer these 4 questions. Okay, sorry, I had to watch ads. All right, we got our first question there. Who invented the modern periodic table? Dmitry Mendeleev. Okay, our next question is, according to the video, why did 1870s table have placeholders? I'm assuming that's coming up. Oh, it just said 1870, so now we're just looking for placeholders. Why did it have placeholders? Okay, so from that, we should be able to answer, why did 1870s table have placeholders? And I want you to answer that in your own way. I'm going to give you a second, and then I'll answer it in my way. Okay, if you need more time, click pause. Okay, so why did it have placeholders? Well, they knew that something was going to go there. We just haven't discovered it yet, or hadn't discovered it yet. Now we have discovered it, and we know exactly what goes on 68. And back then, they didn't know what was going to go on 68. They just knew something went there. So, pretty genius to me. Hold on. We got to look at our third question. What are two things that Mendeleev concluded about the undiscovered Eka aluminum, and how did he figure these things out? Oh, we already know the answers to that. Okay, so two things that Mendeleev concluded about the undiscovered Eka aluminum is that it would have been metal-like, shiny, and it would have had let's go back. I think it was the atomic number of 68. Oh, that was the other thing. It had a really low melting point. Okay, so really low melting point. How did he know those things? Well, he knew it because he was looking at all of the things around it that we did know. Like, we knew what aluminum was. We knew aluminum had a really low melting point. We knew aluminum was a metal. We knew it was shiny. And we knew it could be flattened or stretched, those kinds of things. So that helped him figure out this undiscovered element without even seeing it. Okay, our next question is, according to the video, what was isolated in 1937? Do not put gallium in your mouth. We do have some gallium in the classroom that you'll get to check out, as in look at, and see how it can change from a solid into a liquid. It is fascinating. I love gallium, but I am also a complete science nerd. Just saying, I think science nerd is a super awesome term, and I love being a science nerd, so. All right, that was what was isolated in 1937. It was called technetium. See how we can spell that. Technetium. Technetium. Technetium was isolated in 1937. They're not $5. All right, there was our video. We answered all of our questions. Now let's go back to the PDF. What? Oh, there's my PDF. Okay, scroll back down. Now it says dynamic periodic table. Navigate to the dynamic periodic table website. Use it to answer the following questions. Okay. Look how cool this is. This is so cool. I wish I would have known about this like years ago, and I did not. So I'm gonna click bookmark because bookmarks are the greatest thing ever, and this thing is awesome. Okay, so it says navigate to the dynamic periodic table website. Use it to answer the following questions. Click on hydrogen. Hydrogen. Hydrogen is number 1 if you didn't know that already. It has an atomic weight of what? Well, if we haven't talked about this yet. So, let's see, do I have like a pointer or something? Focus mouse. Oh, that's interesting. I think I want a pen. Okay, pen. All right, so our weight is written out for us right here. It says 1.08. Question, where else do we see weight on our little cube here? 1.008. That is our weight. That is how we can find the weight of any element on the periodic table, is by looking at this number here. Without having it written out here, we can look just at this periodic table and say that cobalt's weight is 58.933. Erase. Okay, so our atomic weight, we should write 1.00 U. Okay. B, what color is it? Now, if you say green, that's unfortunately not the correct answer. Because it is talking about the color on the periodic table. And the color is related to this periodic table in general. If I was to print this on my color ink printer that is currently struggling, it's not going to show up as green. But here it is green. So the color it is talking about is the color that is shown here on the computer screen, which is green. That is not the color of hydrogen. Just saying. What that means is there is a key here, and it means it's a reactive non-metal. If you didn't know this, there is reactivity with hydrogen. Yes, there's hydrogen in the air. That is not reactive, but it is a very reactive element because it likes to bond to so many different elements. It loves bonding. So that's what makes it reactive, and it's not a metal, it's a gas. See, gas. Okay. It also tells us at 0 Celsius, which is 32 degrees Fahrenheit. here's our conversion table up here, and 273 degrees Kelvin. We here in the US use Fahrenheit, so that's probably why they have the conversion there. So at 32 degrees Fahrenheit in America and anywhere, if they use Fahrenheit, that is freezing point. So at freezing point in Fahrenheit, it is a gas. Let's see what it is if we increase the temperature. Oh, I gotta go back to my cursor. How do I do that? Highlight clicks, hide cursor, highlight clicks. Okay, let's make it 100 degrees. 108 degrees is 42 Celsius. It's still a gas. Will it ever not be a gas? Nope, it's always a gas. Oh, wait. It does go to a solid at negative 273 degrees Celsius, which is negative 459 degrees Fahrenheit, which is 0 Kelvin. And that is why we have a Kelvin. Okay. You're never going to see it like that. Sorry. Let's just put this back to 0 by typing it in. Okay. Next question. Meaning in Greek. Hold on, one of my dogs is sticking through the recycling bin. That was Buddy the puppy. Okay. Meaning in Greek. Meaning in Greek. Where do I find meaning in Greek? Anyone else see meaning in Greek? Meaning in Greek. Temperature. Okay, I am not seeing Greek right off the top of my hands or head, so I am going to type in. I clicked Control F to pull up the find, and I'm typing in Greek. Oh, there we go. In Greek, hydrogen means water former. So, C, meaning in Greek, water former. D, boiling point in Celsius. I'm assuming we can find that right here. Boiling point in Celsius is negative 252.879 degrees Celsius, which is negative 423 degrees 0.182 degrees Fahrenheit. I said degrees early, sorry. Okay. That's all we need to know about hydrogen. So we can click the X. How I found that is I clicked the hydrogen, blue hydrogen, underneath write up, and that's what popped up that screen. And right here, it shows you the purple glow in its plasma state, and that is super cool. That's how we get things like neon signs. Neon signs, not all of them are the gas neon. They are actually several different gases, and that's how they produce the color, but the term neon stuck with them. Okay, I am going to go to the next question. It says 6, click on the X on the top right-hand corner. We already did that. Now click on helium. So the way we read the periodic table is the direction that we read. So helium number 2 is over here. Okay. What color is it on this screen, this periodic table? It is purple. Okay, commercial use for it. It is a noble gas. We just mentioned how neon below it is used in neon signs. Helium, what can we think of that has helium gas? I can think of one thing that I rarely ever buy because it's pretty bad for the environment, but helium balloons. We use helium balloons for birthdays and parties and all sorts of things. That is the commercial use for it. There are some other ways that it's used as well. Okay, C, a way that new helium is created. How do we create new helium? Well, first, let's remember atomic number is number 2. Our symbol is now He. Our name is helium, and our weight is 4.026. Now go back to hydrogen. Remember, hydrogen's atomic number was 1. Its atomic symbol was H. Its atomic name is hydrogen, and its atomic weight was 1.008. So go back to helium. And if you ever forget the order, most periodic tables give you a little key for pretty much everything. It does not highlight it like this, though. Okay. Back to helium. Okay, so it says a way that new helium is created. So we can go to helium, and it tells us all about helium. It's in the noble gas group. Its boiling point is lowest among all of the elements. It's the second lightest and second most abundant element in the observable universe. That means the universe that we currently can observe with our technology. We found Greek because it's still in. Oh, right here. Large amounts of new helium are being created by nuclear fusion of hydrogen in stars. I feel like we don't do that here on Earth because we cannot do nuclear fusion of hydrogen in stars on Earth. So, can you see why there is a slow progression of helium disappearing from our Earth? We can't create it here. All right. X out of helium. 7. Go back to the table. Which elements are noble gases? Write the names of all of the noble gases. Okay, so if helium is purple, then everything else that is purple is a noble gas. Now, our super cool periodic table here, we can highlight noble gases by showing the noble gases and putting our cursor over noble gases. And it shows us that it's this line right here. So your answer is helium, neon, argon, krypton, xenon, I think is how you say it. Xenon, sorry, and radon. Okay. 8. Use Google to answer how are the noble gases different from other elements. You must use the word stable somewhere in your answer. There is no need to click a new tab, go to Google, type in which elements are the noble gases. No, sorry, wrong question here. How are the noble gases different from other elements? And then click search and question what's going to pop up. So all we need to do is click on noble gases and it pulls it up for us. The noble gases, historically, also the insert genes, not genes, I'm sorry. The insert, it doesn't even say insert, it says inert gases. Stick with me, guys, stick with me. Inert gases, sometimes referred to as aerogens. Okay. The noble gases make up a class of chemical elements with similar properties. Under standard conditions, they are all odorless, colorless, metamic gases with very low chemical reactivity. The 6 naturally occurring noble gases are helium, neon, argon, krypton, xenon, and the radioactive radon. Oganesson is variously predicted to be a noble gas as well, or to break the trend due to relativistic effects. Its chemistry has not yet been investigated, and so that is why it's unknown, and it's in the row of noble gases because they think that's where it goes, but it's not officially a noble gas. Okay. For the first 6 periods of the periodic table, the noble gases are exactly the members of group 18. Group means the numbers that are counted on this top section here. I'm going to go back so I can show you this section right here. I wish I had like a highlighter. It only highlight clicks for focus mode. Okay, so this section here. Those are your groups. Group 18, that is our noble gases. Okay, let's go back. Okay. Noble gases are typically highly unreactive except when under particular extreme conditions. In the inertness of noble gases, I don't know why I said in the inertness of noble gases makes them very suitable in applications where reactions are not wanted. For example, argon is used in incandescent lamps to prevent the hot tungsten filament from oxidizing. Also, helium is used in breathing gas by deep sea divers to prevent oxygen, nitrogen, and carbon dioxide hypercapnia toxicity. Scroll down. The properties, I still haven't found anything about stability really, so yeah, I haven't seen stable yet, so let's keep going. The properties of the noble gases can be well explained by modern theories of atomic structure. Their outer shell of valence electrons, which is the very outer shell of the electrons, is considered to be full, giving them little tendency to participate in chemical reactions. They don't want to be friends with anybody else because they already have a full life of electrons. Okay, they have all of their valence electrons, which means they don't need anything. They don't want to really give anything away. They are just happy on their own floating around. All right. And it has been possible to prepare only a few hundred noble gas compounds. The melting, okay, he's now in the recycling bin. Just give me a second. Sorry. Okay, so where were we? They're happy, they don't want to go anywhere. The melting and boiling points for a given noble gas are close together, differing by less than 10 degrees Celsius, 18 degrees Fahrenheit. That is, they are liquids over only a small temperature range. Okay, so I know that having a full outer shell of valence electrons being full makes them more stable from my prior knowledge. But let's figure out where it says stable in here. By doing Control F. Okay. Right here. In 1916, Gilbert and Lewis formulated the octet rule, which concluded an octet of electrons in the outer shell was the most stable arrangement for any atom. This arrangement caused them to be unreactive with other elements since they did not require any more electrons to complete their outer shell. Okay, our question was, which of, no, 8. How are the noble gases different from other elements? You must use the word stable somewhere in your answer. So out of everything we've read so far, how are they different from other elements? Well, they have all of their valence electrons filled, which makes them stable. Because they are stable, it makes them unreactive. They are very, very happy little atoms. Happy as in they don't want to gain any electrons because they don't need to, which also makes it where they're very hard to react with other things. All right. Use your own words, don't copy my words. Number 9, which elements are the halogens? Write the names of all the halogens. All right. Halogens, halogens, halogens. Post-transition metals, non-reactive metals, halogens. Halogens. There's not halogens here, which means halogens has to be somewhere else on this periodic table. Can you find it? We just talked about noble gases, so let's go back there. Noble gases. Oh, look, right next to noble gases gives us the halogens. Okay. Halogens is under group number 17, which means it goes all the way down. It's not just the green ones. So, halogens is fluorine, chlorine, bromine, iodine, stannine, tennessine, and that is the answer to that question. Okay, 10. Go back to the dynamic periodic table. Notice, oh, also, if we wanted it to tell us the halogens, we could just click halogens and it tells us which ones they are right there. Okay, go back. 10. Notice that there is a slider at the top right-hand corner. Top right-hand corner. Top right-hand corner. Slider. What is it talking about? This slider? Let's keep reading. This will tell you what elements are in what phase, solid, liquid, gas, at each temperature. It's talking about this. Technically, I wouldn't consider that at the right. It's like almost in the middle, and if it's not entirely at the middle, it's the top left. Okay, ignoring that. This will tell you what elements are in what phase, solid, liquid, gas, at each temperature. At 0 Kelvin, what is the only element in its liquid form? So let me take off this highlighting thing. Turn that on. Okay, So we want to go to temperature 0 Kelvin, which is the K. Okay, so that's what it is. And sorry, 0 K. We have to do it on the slider. We can't do it on the thing. But luckily the slider ends at 0, or it starts at 0 K and ends at 6000 K. So 0 K, the only element did you see it? Helium. So easy to slide off of it. Right there. Helium. Okay, so helium. No, helium. You want to be Kelvin and be at 0. At 0 Kelvin, what is the only element that is in liquid form? Liquid helium. There we go. It was right. Okay. B, at 5,845 Kelvin, what is the only element that's in liquid form? Okay, well, we know that it ends at 6000 Kelvin, so 500, 800, I did it again, 5,845. 5,845. Super close. Go up one. A little bit. Okay, 45. Click it. Why is it not highlighting? Okay, so in that section, the only thing that is popping up is rhenium. 75, it's right here. And if we click it and we type in 5,845, it should say that it's a liquid. Sorry, that it's a liquid. And that is true. Okay, so we got that right. C, why are elements 104 and 118 grayed out? 104 through 118. It's talking about this section here. Why are they gray? So if you see their symbol is gray, and for 109 to 118, the entire thing is gray or white. So why are they grayed out? Will it let us click on the number? No, so it's not that. What can we find out if we click Rutherfordium? It's a synthetic chemical element. Okay. What about this one? Methanuranium. Synthetic chemical element. I'm seeing a pattern here. Okay, what about the one that was under the noble gas? Synthetic chemical element. All right, that must be our answer. Those are all synthetic chemical elements. That means that they can be created in a really expensive lab. 11. Navigate to the Khan Academy periodic table, electron shells and orbitals. So that is up here, I believe. That's what it's talking about. I actually don't think that's what it's talking about. Let's go back to the PDF, scroll down to where we're at. It says right here, Khan Academy, periodic table, electron shells, and orbital. Takes us to Khan Academy. No, you don't need to contribute to Khan Academy and the effort of COVID. Okay. Introduction. We want to be on the periodic table, electron shells, and orbitals. Okay, as you read it, answer the following questions. Where in each element's square is the atomic number written? We already learned that. Go back to our periodic table. Where in the square is our atomic number written? Go back to our key. It's the top number, whatever is at the top. Okay, so it is the top number in the square. B, what is the electron shell closest? If we were to read this, I'm sure it's in here somewhere. Periodic table. When I was in high school, we had to memorize every single element and its order in the periodic table, not including the synthetics. I won't make you do that. Oh, there we go. As well as its atomic number 1 in the upper left-hand corner. It is relative atomic mass of 101. Okay, so that's where we find it on the Khan Academy sheet. B, what is the electron shell closest to the nucleus called, and how many electrons can it hold? Hey, look, it has it written out for us. Electron shells and the Bohr model. Right here. Where does that sentence start? By convention, each shell is assigned a number and a symbol n. For example, the electron shell closest to the nucleus is called 1n. All right, so our answer is 1n. Now, if you don't know a whole lot about chemistry and this is your first class, I really want you to go through and read this section because it is important and it gives you a deeper understanding, which will give you a deeper understanding of the class as well. But I don't want to make the video as long as it takes me to read, so I'm gonna refer you to read on your own and just show you how to do some quick research skills. Okay. So we learned that the shell closest to the nucleus is called 1n. C, what is the name for any element's outermost shell? Any outermost shell, we learned from the last thing we read about noble gases, was they are called valence electrons. Which means it is called the valence shell. That is what I am assuming. Let's see where we can find it. Oh, the number of electrons in the outermost shell of a particular atom determines its reactivity or tendency to form chemical bonds with other atoms. This outermost shell is known as the valence shell. The electrons bound in it are called valence electrons. In general, atoms are most stable, least reactive when their outermost electron shell is full, hence noble gases. Most of the elements important in biology need 8 electrons in their outermost shell in order to be stable, and this rule of thumb is known as the octet rule. Some atoms can be stable with an octet even though their valence shell is in the 3n shell, which can hold up to 18 electrons. We will explore the reason for this when we discuss electron orbitals below. Okay. What is the octet rule? The octet rule is when the outermost, right here, the need, no, okay. This rule of thumb is known as the octet rule. So 8 electrons in their outermost shell in order to be stable is known as the octet rule. Okay. 12. For the following elements, draw their Bohr model diagram: hydrogen, carbon, neon, chlorine. Group 1, hydrogen, Bohr model. This is a Bohr model. I remember it as the circle with P's. Okay, so it wants you to draw the circle with one P. And as a P, I'm talking about P the vegetable. You could also call it a bead. It is technically an electron. So the ring with one electron is hydrogen. So draw that on hydrogen. Okay, our next one is carbon. I know that carbon, if I don't know its symbol, then I can find it here on the periodic table. And carbon is right here. Its symbol is C. So C, draw this model right here. You have 2 electrons on the first shell, which is the maximum allowed electrons on that shell in the Bohr model. Then you get a second shell because you will have a full first shell. So you need a second shell. Okay, so our second shell can hold 8 electrons, but carbon does not need 8 electrons, and we get its electrons from its atomic number, 6. Go back. 1, 2, 3, 4, 5, 6. Okay, let's try and see if that worked for hydrogen. Hydrogen has 1 atomic symbol. 1 atomic symbol equals 1 electron. So electrons equals atomic symbol. Remember that. Okay, so 6 electrons. First 2 are on the first shell. That's the maximum the first shell can have. Second shell, we spread it out equally. So you want to put 1 electron and then your next one, and then is actually not here where my cursor is. It is balanced, so you want to put it across from each other. If you have 3, now this is where it's not technically balanced in the Bohr model, and you can see that by the ones over here where it's just one lonely one. So it goes 1 and then another one and another one. Okay, so that gives us carbon here. So we have 6 electrons, and on our second outer shell, which is currently our valence shell, because it's the most outer shell of carbon, we have 4 electrons, and they are spread out equally. Okay, so draw that model in your little circle. Now we have neon. Neon we already looked at, and it has a symbol of Ne. And let's look at what our atomic number is, 10. So we should have 10 electrons in our shells. However, our first shell can only have 2 electrons. So we have our 2 electrons there. Then we need to put our next electrons on our next shell. The next shell can only take 8 electrons. 8 electrons. Okay, so we have 1, 1, 2, 2, which makes 4, plus our 2 in the middle. So now we have 5, 6. Okay, 7, 8, 9, 10. I am going to draw this out for you so you can see what it looks like to draw and figure it out. We got, and I'm drawing with my mouse, so bear with me. It's a finger mouse, not a hand mouse. Okay, so we have our first shell. That's terrible circle. 1 electron, 2 electron. Okay, we know that there is 10 electrons, so there has to be another shell. Start at the top, 1 electron, which means 3 electrons, 4 electrons, 5 electrons, 6 electrons. I know that my shell is half full because this shell can contain 8. So let's draw our nucleus here, our second shell. Second shell, remember, can have 2 electrons. Our third shell can have 8 electrons total. Okay, so right now we are at 1, 2, 3, 4, 5, 6, 7. We know that neon needs 10. 8, 9, 10. All right, we got neon. Okay, chlorine. Chlorine. Okay, chlorine is right here. Oops. Pointer. Chlorine. It has an atomic number of 17. Atomic number means electrons, and that means it must have 17 electrons. Okay, so if we have completed the amount of electrons in neon that we can have in our second ring, that means we need another ring. I feel like I should change the colors. So here, the nucleus is green now. Green. Okay. And dark blue will be the first ring, and purple is our second ring. Sorry, I should have done this first. 8. Oh, I cannot copy. Okay. And our third ring is going to be orange. Third ring. Okay. I am quite certain that the third ring, oh, that's cool. My drawing goes with it. Is 18. Subshells and orbitals. Tells us the letters which are given to those orbitals. So the first orbital, it has a drawing here for you. Our first orbital is the S, which is your first 2. And then you go to P, And then the next one is D and F. Currently ignore this shape right here. This is just showing you how orbitals in a molecule actually look, and that they are not flat like we are drawing in the Bohr model. Okay, so here's our Bohr model. And if we go out, then energy must be absorbed. But if we are going in, energy is released. Our first ring is called 1n, our second ring is called 2n, and our third ring is called 3n. So we want to know how many electrons are allowed in 3n. Okay, 2n can hold 8. Third shell, 3n, can hold up to 18. Where's our drawing? Okay, so our third one is 18. E stands for electrons. Okay, so we know neon there is done. And we want to do chlorine. And chlorine had 17 electrons. So first we would draw chlorine. Hold on. Let me continue my color coding for you. So chlorine, symbols, and create its nucleus. Then we need to do our second layer, which we had as blue. Second layer can only take 2 and actually should be a circle, but pretend that's a circle. And I didn't want to do that because Bohr model starts at the top. 1, 2. Okay, 2 electrons on first shell, 1n. Now we need second shell, which we had as purple. That can have 8. Neon had a number of 10, so we know that there is 10 electrons here. 10 total. Tote. Okay, so we know that the second ring is completely filled. So it really doesn't matter which way you put on these electrons, as long as you get all 8 there, because you're going to need that third shell. I'm gonna scroll up just a tad so that way I can put in my third shell, which is our outer shell, which remember is called your valence shell. And we labeled that as orange. Shell 3n has 18. We are at 10 right now, and chlorine had a number of 17. So 10, we need 7 more. So 1, 2, 3, 4, 5, 6, 7. All right, so that is how we get chlorine, which is also found right there, which is much prettier than my drawing with my mouse. Sorry. Okay. Hopefully you made a much prettier representation on your paper. Now, question 13 is, why do scientists say Bohr models aren't actually great representations of electron orbitals? Prove your point by drawing what some orbitals actually look like. So, that is where it says right here, the Bohr model is useful to explain the reactivity and chemical bonding of many elements, but it actually doesn't give you a very accurate description of how electrons are distributed in space around the nucleus, which means it doesn't give you an accurate representation about how that atom actually looks with its electrons around it, because again, it is not a circle with dots next to each other. It does make it easier for us to draw though. So particularly, I like to draw the Bohr model, especially when I'm trying to see the electrons. But if we want to see them in space around the nucleus, then we need to use a different model. So specifically, electrons don't really circle the nucleus, but rather spend most of their time in sometimes complex-shaped regions of space around the nucleus, known as electron orbitals. We can't actually know where an electron is at any given moment in time, but we can mathematically determine the volume of space in which it most likely is to be found. Say the volume of space in which it will be spending its time is 90%. The high probability region This high probability region makes up an orbital, and each orbital can hold up to 2 electrons. So how do these mathematically defined orbitals fit in with the electron shells we saw in the Bohr model? We can break each electron shell down into one or more subshells, which are, you shouldn't be yawning. I'm yawning because it's 11 o'clock at night. You shouldn't be yawning. Okay. Subshells are designated by the letters S, P, D, and F. And each letter indicates a different shape. For instance, S subshells have a single spherical orbital, while P subshells contain 3 dumbbell-shaped orbitals at right angles to each other. Most of organic chemistry, the chemistry of carbon-containing compounds, which are central to biology, involves interactions between electrons in the S and P subshells. So these are the most important subshell types to be familiar with. However, atoms with many electrons may place some of their electrons in D and F subshells. Subshells D and F have more complex shapes and contain 5 and 7 orbitals respectively. And then it gives us our example. These right here, the X, Y, and Z, that is just telling you what plane it's in. So Y goes this direction, X goes that direction, and Z goes this direction. I wish it would allow you to highlight what those look like. So let's go back. Oh, let me turn off my marker to the electrons. And if you see right here, we are on here. It gives you what subshells it is in and how to write it. So you first have to take up 1s, which is hydrogen. And then if you go to 2s, you have to have 3 electrons. So 1 electron, 1s. 2 electrons, 1s2. 2, we're on 2. So an easy way that I always remembered it is these shells correlate with these numbers for the most part. So if we're on 2, then 3 is 2s1, 2s2. So if we were to write this in expanded form, it would say 1s2, and that 2 is superscript, and then 2s2. That represents that we have 4 electrons and what shells they are in. Okay, so that is super complicated. You really don't have to remember that. At least we aren't going to be going into it in our class, but in college you will go into it. So just giving you a heads up on that. I really wanted to be able to show you kind of what those orbitals looked like highlighted, but I don't think this one is going to show us. But it does kind of show us in some forms what these more complicated ones look like in space over with this image. So if you want to take a look at that. It does say that we should draw this drawing on number 13, and it gives us very little space to do that, so try your best. All right, don't forget to let me know that you participated in this video, and mark that by saying a comment on either the Google Classroom assignment or the Google Classroom stream, or the Mrs. Shears Secondary Science channel in Slack. You can add an emoji for which class that you participated in. And this is chemistry. All right, we covered a lot today, so if you need to watch this video multiple times, do it. If you want to find more videos, I personally love SciShow and their other videos that they have. Along with SciShow, they have another channel. Okay, so their other channels are SciShow for Kids, Crash Course for Kids, and Crash Course Normal, and then they have so many more. Other ones that I like is Minute Earth. That one is really, they use a lot of drawings, and I like that about them. Crash Course, it goes really fast, so typically I either slow it down or pause a lot. And there's just tons of other ones that we can go into. But I personally like the Crash Course and SciShow, and they have a lot on chemistry as well. So, and that's all I have for you. All right, bye.